4 that introduced Genie, the model that turned heads in the world of generative AI. Now that Google has released Genie 3, it's the perfect time to go back and explore what made the original Genie so special. At its core, Genie is all about creating interactive, playable virtual worlds from just a simple prompt, whether that's a photo, a sketch, or even a text-to-image model. What makes this so remarkable? Genie learned to generate these environments without needing any labeled actions or text, simply using millions of unlabeled videos. It uses a neat trick called latent actions, which lets users control the world frame by frame. Let's dive in and see how this innovation set the stage for what we now have in Genie 3.
All right, let's dive into our first section. We're talking about Genie, this amazing model that creates interactive environments from scratch. Imagine it as a magic wand that transforms text, sketches, or photos into virtual worlds you can play in. The fascinating part? Genie learns from the internet without needing labeled data, a big win for model training. Now, Genie uses a special action space learned from online videos to let users interact with these worlds. It's like having a remote control for a game that's created in real time based on your input. Look at the figure here. You start with a prompt, maybe a sketch or a photo, and Genie turns it into an interactive scene. You can tweak it using different actions, represented by gaming controllers. Neat, right? Genie is powered by 11 billion parameters and is built with advanced components like a video tokenizer and an auto-regressive model. These help it understand and predict action sequences. The goal? To train agents that mimic unseen video actions, paving the way for more generalized AI agents. Exciting stuff! Now that you have the gist of Genie, let's talk about the rise of generative AI. Thanks to technologies like transformers, these models have evolved to create not just text or images, but now videos and interactive experiences. This is where Genie steps in, offering a new perspective by generating interactive environments from simple prompts. Imagine having 200,000 hours of gaming videos at your disposal. Genie uses this data to learn and predict interactions without detailed annotations. Despite its hefty 11 billion parameters, it's efficient, generating virtual worlds from unseen images. Look at the figure here. Genie starts with a generated image or sketch, and produces frame sequences influenced by user-driven latent actions. This means you interact with these environments in real time, making them dynamic and engaging. Genie is scalable. Its sophisticated architecture handles massive data effortlessly, hinting at potential for even larger models. And it's not just limited to game data. It's tested on robot videos too, demonstrating its versatility. This could be pivotal for developing more general AI systems. Let's break down the methodology behind Genie. Check out the comparison table. Genie stands out because it only needs video data to control environments at the frame level, unlike others requiring actions or text. So how does Genie work? It's built on video-only data, using components inspired by the Vision Transformer. This tackles the memory challenges of processing video data. The architecture uses an ST transformer, which employs space-time blocks for efficient memory management. This makes it scalable, even with more frames. Now let's talk about Genie's core components. We have three main parts: a latent action model predicting actions between frames, a video tokenizer converting frames into tokens, and a dynamics model predicting the next frame using these tokens and actions. It's a two-phase training process, starting with the video tokenizer, then co-training the other components. The key is the latent action model, predicting future frames from past frames using VQVAE techniques. This allows Genie to generate dynamic, interactive environments from internet videos without explicit action labels. Pretty neat, right? Let's see how Genie's components work together. Take a look at Figure 3. The training process begins by breaking video frames into smaller, discrete tokens using a video tokenizer. Genie then infers latent actions, predicting what happens between frames. These tokens and actions feed into a dynamics model that predicts the next frames. Moving to Figure 4, we see the ST transformer architecture. It uses space-time blocks with layers for attention in both space and time, processing video data efficiently. Each color shows how different video parts are attended to over time. Now Figure 5 shows the latent action model. It learns actions from videos without needing labeled data, using an encoder-decoder approach. This means it can predict actions just by watching videos. Finally, Figure 6 focuses on the video tokenizer, using a VQVAE with the ST transformer to compress and encode video data, capturing temporal dynamics. This makes video generation more robust and efficient. Unlike older methods focusing only on spatial compression, this considers time, handling long video sequences better. Together, these components make Genie a powerful tool for generating interactive environments. Now let's dive into how Genie uses its dynamics model and performs inference. Look at Figure 7. Here, the dynamics model, a specialized transformer, takes video tokens and latent actions as input, predicting what happens next. It uses cross-entropy loss to compare predicted and actual frames, ensuring accuracy. Next, check out Figure 8. This is where Genie becomes interactive. You start with a prompt frame, your starting image. It's tokenized to create a starting point. Then, you choose a latent action, like selecting a command from a menu. This guides how the video evolves, with the dynamics model predicting future frames based on your choices. In the experiments section, Genie is tested on a massive dataset of platform game clips. This provides a rich variety of scenarios for Genie to learn from. The results show Genie, with its 11 billion parameters, can generate new and continuation videos by selecting different latent actions. This makes it a powerful tool for creating dynamic, interactive environments where users can experiment with different outcomes. Let's explore Genie's scaling and performance metrics. Look at Figure 9, which shows how Genie performs across different model sizes. The left part tracks training progress over time, while the middle and right parts detail final training losses, giving insights into efficiency and effectiveness at different scales. Genie's adaptability to different data sources, including a robotics dataset, shows its potential to generalize across various data types without action labels, treating everything as video input. The metrics used to evaluate Genie focus on video quality and control. For video quality, they use the FVD, aligning well with human evaluations. For control, there's a special metric called delta PSNR, measuring how well Genie's generated videos align with expected outcomes when conditioned on inferred actions. Training details are crucial. The video tokenizer uses 200 million parameters, and Genie balances reconstruction quality and prediction performance. The latent action model and other components are finely tuned, ensuring smooth operation across scenarios, making Genie scalable and versatile. This highlights Genie's robustness and adaptability, making it a formidable tool in generative AI. Let's see how Genie handles image prompts and model performance. Look at Figure 10. It showcases Genie's flexibility, starting from various image prompts, text-to-image outputs, sketches, or real photos. Each example moves from an initial image to a dynamic action sequence, showing character movement through scenes. This adaptability highlights Genie's ability to work with diverse visual inputs, even those different from its training data. The page discusses how scaling impacts Genie's performance. Increasing model and batch sizes improves outcomes, as seen by reduced training loss. A larger model at 10.7 billion parameters shows how scaling both sizes yields better results, making Genie more robust and capable. In the qualitative results section, Genie is evaluated with out-of-distribution prompts, meaning it was tested with images not seen during training. This showcases its ability to generate high-quality, controllable videos across domains, crucial for demonstrating Genie's robustness and potential applications in various fields. Overall, this highlights Genie's strength in handling diverse inputs and scaling efficiently to produce dynamic, interactive environments. Let's dive into Genie's handling of complex scenarios and consistent actions. Look at Figure 11. It shows Genie simulating deformable objects, like a bag of chips, learning and replicating physical properties in a dynamic environment. Moving to Figure 12, we see Genie emulating parallax, a technique in platformer games for depth by moving foreground and background elements at different speeds. This showcases Genie's understanding of 3D scenes, enhancing realism. Figure 13 takes us to robotics, where Genie demonstrates consistency in action across diverse frames. Despite lacking action labels during training, Genie maintains semantic actions like moving down, up, or left, showing its robustness and adaptability. The page concludes with Genie's potential as a foundational tool for training agents in reinforcement learning. By generating diverse trajectories and understanding complex scenes, Genie could revolutionize machine learning in dynamic settings. This adaptability opens doors for broader applications, from gaming to robotics, emphasizing Genie's role in advancing generative AI technologies. Let's explore Genie's adaptability and performance in various environments. Check out Figure 14. It illustrates Genie's capability to generate diverse pathways in a new reinforcement learning setting, highlighting its flexibility and ability to adapt without prior exposure. Figure 15 showcases behavioral cloning experiments, Here, Genie LAM is compared with random and Oracle models in a platformer environment. Genie matches the Oracle's performance with far fewer samples, proving its efficiency and adaptability. Look at Table 2, which compares different input methods for the latent action model. It shows Genie, using pixel inputs, achieves better control and performance across datasets, underscoring the importance of input choice. Moving to Table 3, various tokenizer architectures are compared. The standout is ST-VVT, balancing memory use and performance, achieving impressive metrics in video dynamics and quality. This reveals the importance of selecting the right architecture for optimal results. Overall, this page emphasizes Genie's robust design choices and adaptability, making it a powerful tool in generative AI, especially for dynamic environments and tasks requiring high controllability and efficiency. Now, let's dive into the architecture and related work behind Genie's approach. The ST-VVT architecture shines by balancing high-quality video generation with reasonable memory use. It outperforms others like C-VVT, showing Genie's ability to create videos with fidelity and controllability. This success highlights the importance of efficient design in handling complex video data without overfitting. In the related work section, Genie is placed within the broader context of world models, predicting future frames based on learned actions, useful for training agents without direct experience. Unlike traditional methods needing specific action data, Genie learns from video alone, making it versatile and scalable. Genie extends playable video generation by allowing interactions with generated environments. This contrasts with domain-specific approaches, offering more flexibility and adaptability. Additionally, Genie's work relates to procedural content generation, where ML aids in creating game levels. Here, Genie stands out by using video data directly, leveraging the vast diversity online. Ultimately, Genie's design and adaptability set it apart, making it a robust tool in generative interactive environments. Finally, let's wrap up with Genie's conclusion and future outlook. The potential here is huge. Genie generates interactive environments without needing labeled action data, learning from videos, which is cost-effective and flexible. It can create diverse, controllable worlds, similar to those crafted by humans, opening creative possibilities for users of all ages. However, challenges remain. Genie inherits limitations from autoregressive transformer models, like hallucinating unrealistic scenarios. It's also limited to a short memory span, affecting consistency over long actions. Plus, 1 frame per second isn't ideal for real-time interactions. The potential for future research is immense. Genie could be scaled to use more internet video data for simulating diverse, realistic environments. It could also significantly impact training agents for reinforcement learning by providing rich, varied environments. Genie's broader impact is exciting. It allows anyone to create and explore virtual worlds, fostering creativity and innovation. The hope is that as technology advances, Genie can further amplify human creativity, making world-building accessible and engaging for everyone. Thanks for joining us today. Happy exploring together.